Every single day, more than 100,000 aircraft take to the skies. Millions of people board airplanes without giving it a second thought. A boarding pass is scanned, the cabin doors close, the engines roar to life. A machine weighing hundreds of tons accelerates down a runway, and within seconds, it rises effortlessly into the sky. We watch it happen almost every day, so often that we've stopped asking perhaps the most extraordinary question of all. How? How can something so unimaginably heavy leave the ground? How can an object made almost entirely from metal stay suspended in the air for thousands of kilometers? How can a machine carrying hundreds of passengers cross entire oceans without ever touching the ground? Today, flight feels ordinary, but for nearly all of human history, it was considered impossible. Not difficult, not expensive, impossible. For thousands of years, humanity watched birds disappear into the clouds while remaining forever trapped on the earth below. Kings dreamed about it, scientists obsessed over it, inventors dedicated their entire lives to it. Some became legends, many failed spectacularly. Some even lost their lives chasing a dream that seemed forever beyond human reach. Yet despite centuries of failure, humanity refused to give up. Because every generation believed one thing: if birds could do it, then perhaps, one day, so could we. This is the story of how humanity conquered the sky. The first pilots. Long before airplanes, before engines, before propellers, the greatest pilots on Earth already existed. Birds. They could climb higher than mountains, travel across entire continents, ride invisible currents of air without flapping a single feather. To ancient humans, this ability seemed almost supernatural. Imagine standing on an open plain thousands of years ago. There are no skyscrapers, no satellites, no helicopters, no drones. Nothing has ever left the ground except smoke and birds. You look upward. An eagle circles effortlessly above a mountain. Moments later, it disappears into the clouds. No roads, no bridges, no obstacles, complete freedom. For early civilizations, flight wasn't simply transportation. It represented power, freedom, perfection, and even divinity. Many cultures believed only gods deserved the sky. The heavens belonged to beings greater than mankind. Humans were creatures of the ground. When myths became dreams. Long before science existed, stories tried to answer questions that nobody could explain. One of those stories has survived for thousands of years. It tells of a master craftsman, Daedalus, and his son, Icarus. Trapped on an island with no escape by land or sea, Daedalus looked upward. If the earth offered no path to freedom, perhaps the sky did. According to legend, he collected feathers from birds, bound them together with thread, sealed them using wax, then constructed two enormous pairs of wings. Before taking flight, he warned his son, "Do not fly too low, or the sea will soak your wings. Do not fly too high, or the sun will melt the wax." But overwhelmed by excitement, Icarus ignored the warning. Higher, 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 until the wax softened. The feathers drifted away. The wings failed, and he fell into the sea. Whether true or not was never the point. The story survived because it captured something deeply human: our willingness to risk everything for the chance to fly. Copying nature. As centuries passed, humanity slowly stopped asking, "Can we fly?" Instead, people began asking, "How do birds fly?" That tiny change transformed fantasy into science. People began studying wings, feathers, gliding, takeoffs and landings. Some believed copying birds exactly would unlock the secret. Others attached giant wooden wings to their arms. Some climbed towers, hoping they could flap their way into history. They couldn't, gravity always won, again and again and again. The problem wasn't courage, the problem was understanding. No one knew what lift was. No one understood airflow. No one had discovered the invisible forces acting on every wing. Without realizing it, they were trying to solve one of the most complicated engineering problems in history, using almost no scientific knowledge. Leonardo da Vinci, the man who saw the future. Then, in 15th century Italy, everything changed. A man named Leonardo da Vinci looked at birds differently from everyone else. Most people admired them. Leonardo investigated them. He wasn't satisfied with saying, "Birds can fly." He wanted to know why. Hour after hour, day after day, he observed birds soaring through the Italian countryside. He watched how wings twisted, how feathers adjusted during turns, how birds landed without crashing, how they climbed against the wind. His notebook soon filled with hundreds of sketches, flying machines, parachutes, helicopter-like aerial screws, gliders, mechanical wings. Most of these inventions never flew, not because the ideas were wrong, but because the world wasn't ready. Wood was too heavy, metal was too crude. Human muscles couldn't generate enough power. Engines had not yet been invented. Yet Leonardo achieved something even more important than flight itself. He changed the question. Instead of asking, "Can humans fly?" he asked, "What laws of nature make flight possible?" That single idea would inspire generations of engineers long after his death. The first breakthrough. For centuries, everyone believed the answer lay in flapping wings. But nature had been hiding another solution, one that birds used every single day. Not all birds flap continuously. Watch an eagle carefully. It spreads its wings, then simply glides. No frantic movement, no constant effort, just smooth, effortless flight. The secret wasn't flapping. It was the shape of the wing and the movement of air around it. Humanity didn't realize it yet, but this observation would eventually change the world. Instead of building giant mechanical birds, engineers would begin building machines that allowed the air itself to do most of the work. That realization marked the birth of modern aerodynamics, and although nobody knew it yet, the age of true flight had finally begun. While inventors struggled to imitate birds, another group of dreamers was quietly pursuing an entirely different path. They weren't trying to fly through the air. They wanted to float above it, using nothing more than hot air. And their success would prove something humanity had never demonstrated before: that human beings could leave the ground and survive. When humans first left the Earth, for thousands of years, humanity dreamed of flight. But dreaming and leaving the ground were two completely different things. For centuries, inventors focused on one idea: if birds flew by flapping their wings, then humans should simply build bigger wings. The result was almost always the same: failure. Some machines barely left the ground, others never moved at all. Many inventors were seriously injured, some never lived to try again. Nature had hidden her greatest secret well. Humans were trying to imitate birds without first understanding the sky itself. Ironically, the first successful human flight would not come from copying birds at all. It would come from understanding something far simpler: heat. Imagine standing in a small French village during the summer of 1783. News has spread quickly. A strange machine is about to rise into the sky. People gather from miles away. Some whisper that it is impossible. Others believe it must be magic. Children stare in amazement. Farmers stop working. Even nobles arrive to witness the spectacle. In the center of the crowd stands an enormous fabric balloon. Beneath it, workers feed a roaring fire. Slowly, something extraordinary begins to happen. The balloon rises, not because it has wings, not because it has an engine, simply because the air inside it has become hotter than the air surrounding it. For the first time in recorded history, humans watch a machine lift itself away from the Earth. No bird, no myth, no miracle, but an invention. The dream of flight had taken its very first breath. The inventors behind this remarkable achievement were two French paper manufacturers, Joseph Michel Montgolfier and Jacques-Étienne Montgolfier. The Montgolfier brothers had spent years experimenting with heated air. At the time, many people believed smoke itself caused objects to rise. In reality, the secret was much simpler. Hot air is less dense than cold air. As air heats up, its molecules spread farther apart. The same volume of air now weighs slightly less. That lighter pocket of hot air is pushed upward by the cooler, denser air surrounding it. The balloon doesn't pull itself into the sky. The atmosphere pushes it upward. Without realizing it, the Montgolfier brothers had demonstrated one of the most beautiful principles in physics. Sometimes, the easiest way to fly isn't by fighting gravity. It's by letting nature do the lifting. The first passengers. Before risking human lives, scientists chose safer volunteers, a sheep, a duck, and a rooster. Together, they became the first living passengers ever carried into the sky by a flying machine. Thousands watched as the balloon climbed higher and higher. The crowd held its breath. Would the animals survive? Minutes later, the balloon landed safely. The passengers were unharmed. Human flight suddenly seemed possible. Only months later, people themselves climbed aboard. History had changed forever. For the first time, human beings looked down upon the Earth from above. Cities appeared smaller. Roads became tiny lines. Rivers looked like ribbons winding through the countryside. The world had never been seen from this perspective before. Flight had changed not only transportation, but human perception itself. But balloons had one enormous weakness. They could go up. They could come down. They could drift. They could not truly fly. The wind decided everything. Imagine boarding an airplane today, only to discover the pilot has no steering wheel, no rudder, no engines. Wherever the wind chooses, that's where you go. Cross a mountain, maybe. Land safely, hopefully. Avoid a storm, impossible. Balloons proved humans could leave the Earth, but they could never provide controlled flight. To conquer the skies, humanity needed something far more sophisticated: control. The father of the airplane. While balloons floated wherever the wind carried them, one English engineer was asking a much deeper question: Sir George Cayley. Today, many people have never heard his name, yet modern aviation exists largely because of his ideas. Unlike earlier inventors, Cayley stopped obsessing over flapping wings. Instead, he asked a revolutionary question: what actually keeps something in the air? He separated flight into individual engineering problems: lift, weight, thrust, drag. That might sound obvious today, but around the year 1800, this way of thinking was revolutionary. Rather than copying birds, Cayley began studying forces. He built experimental wings, tested different shapes, observed airflow, measured performance. Eventually, he proposed something astonishing: an aircraft should have fixed wings, a separate propulsion system, and a separate control system. That simple concept forms the foundation of virtually every airplane flying today. In many ways, Cayley designed the modern airplane long before engines were powerful enough to build one. Learning to glide. As the 19th century progressed, inventors across Europe became obsessed with gliders. Unlike balloons, gliders offered something humanity had never possessed: control. One of the greatest pioneers was a German engineer named Otto Lilienthal. Rather than hiding in workshops, he climbed hills again, and again, launching himself into the air hundreds, then thousands of times. Each flight lasted only seconds, but every landing taught him something new. He carefully documented wing shapes, balance, center of gravity, airflow, and lift. For the first time, flight was becoming experimental science rather than hopeful guesswork. Sadly, Leonardo eventually crashed during one of his flights and later died from his injuries. Many believed his death marked the end of mankind's dream. Instead, it inspired the next generation. Among those studying every page of Leonardo's research were two bicycle mechanics from Ohio. Neither possessed university degrees. Neither had government funding. Neither had ever built an airplane. Yet together, they were about to achieve what humanity had pursued for thousands of years. Their names were Wilbur and Orville Wright. The year is now 1903. The location, Kitty Hawk, North Carolina. A lonely stretch of sand, strong winds, towering dunes, and one fragile wooden machine. Everything humanity had learned over thousands of years had led to this single moment. Would it fly? Or would it become just another forgotten invention buried beneath history? Only 12 seconds separated success from another failure. A freezing wind swept relentlessly across the empty sand dunes. The Atlantic Ocean crashed against the shoreline, each wave drowned by the howl of a bitter winter breeze. There were no grandstands, no reporters, no flashing cameras, no cheering crowds waiting to witness history. Only 5 local men, 2 brothers, and a peculiar wooden machine sitting on the cold sand. Its wings stretched over 12 meters from tip to tip, covered in tightly woven muslin fabric. A lightweight gasoline engine sat beside the pilot. Twin wooden propellers waited silently behind the wings. It looked fragile, impossible. No one standing there could have imagined that within minutes, human history would divide itself into 2 eras: before powered flight and after powered flight. History often remembers success. It rarely remembers the thousands of failures that made success possible. For centuries, inventors believed the greatest obstacle was power. If only we had a stronger engine. If only we could flap harder. If only we could build larger wings. But they were solving the wrong problem. The greatest challenge was never leaving the ground. It was staying in control once you did. Imagine balancing a bicycle. Moving forward is relatively easy. Keeping your balance, steering, and recovering from a sudden gust of wind. Those are the difficult parts. Now imagine trying to balance. Not onto wheels, but in the air, with invisible forces pushing against your wings from every direction. That was the real challenge, and nobody had solved it. Aircraft could lift briefly. Some gliders could even travel impressive distances. But once disturbed by turbulence, they became almost impossible to control. Many crashed within seconds, some flipped over completely. Others stalled without warning. The sky wasn't forgiving. Every mistake had consequences. The wind tunnel. By 1901, something bothered Wilbur Wright. Existing aerodynamic tables didn't match reality. According to published scientific data, their gliders should have generated far more lift than they actually did. Either their experiments were wrong, or the world's accepted data was wrong. Most inventors would have trusted the books. The Wright brothers trusted evidence. So instead of arguing, they built their own wind tunnel. It wasn't large, it wasn't expensive, but it became one of the most important scientific instruments in aviation history. Inside the tunnel, they tested hundreds of miniature wing designs. Different curves, different angles, different shapes, hour after hour, day after day. They measured lift, drag, airflow, efficiency. Unlike previous inventors, they weren't guessing anymore. They were collecting data, real data, accurate data, By the time they finished, they possessed the most reliable aerodynamic information ever gathered. For the first time, the dream of flight rested not on hope, but on science. The brothers now had something every inventor before them lacked: reliable knowledge. Next, they needed an aircraft. Weight became the enemy. Every unnecessary kilogram reduced their chances of taking off. Commercial automobile engines were too heavy, so they built their own. With the help of their mechanic, Charlie Taylor, they designed a lightweight 4-cylinder gasoline engine capable of producing around 12 horsepower. By modern standards, that sounds tiny. Some lawnmowers today produce similar power. Yet those 12 horsepower would change history. Next came the propellers. Surprisingly, very little research existed. No one truly understood how to design an efficient aircraft propeller. Once again, the brothers solved the problem themselves. Rather than thinking of a propeller as a spinning fan, they realized it behaved more like a rotating wing. Each blade generated lift, except that lift pointed forward. That insight allowed them to design propellers far more efficient than anything that existed at the time. Even today, engineers still admire just how advanced those designs were. Finally, everything was ready. The Flyer, a machine built from spruce wood, muslin fabric, steel cables, an engine, and thousands of hours of relentless experimentation. For 12 unforgettable seconds, the impossible became reality. The aircraft traveled approximately 120 feet before gently returning to the sand. 12 seconds. That was all. Yet within those 12 seconds, human civilization changed forever. History has a funny way of treating revolutionary ideas. At first, it ignores them. When the Wright brothers announced they had successfully flown a powered aircraft, many newspapers simply refused to believe the story. Some editors thought it was another exaggerated invention. Others believed that if such a machine truly existed, someone more famous would have built it first. After all, how could two bicycle mechanics accomplish what the world's greatest scientists had failed to do? Even the American government showed little interest. Ironically, Europe became far more curious than America itself. The Wright brothers continued improving their aircraft quietly. Every new version flew farther, longer, higher, more reliably. Their goal was never simply to leave the ground. Their goal was to build an airplane people could actually use. Once powered flight became reality, the race began. Inventors around the world joined the challenge: France, Germany, Britain, Russia, Italy, and the United States. Every nation wanted faster aircraft, higher aircraft, safer aircraft. Engineers competed fiercely. Aircraft evolved almost yearly. Wings became stronger. Engines became more reliable. Pilots became bolder. Flight records were broken one after another. Altitude, distance, speed, endurance. Every new achievement inspired another. Humanity had entered the age of aviation. When war changed aviation forever. Then, everything changed. In 1914, the world was plunged into the First World War. At first, aircraft played only a minor role. Pilots flew over enemy positions observing troop movements. Their greatest weapon was information. But war has always accelerated technology. It wasn't long before airplanes became weapons themselves. Pilots carried pistols, then rifles, soon machine guns, bombs, stronger engines, more powerful aircraft. Governments poured enormous resources into aviation. Engineers suddenly had funding, factories, and urgency. Aircraft that once struggled to remain airborne were now climbing thousands of feet above battlefields. The pace of innovation exploded. Engines doubled in power. Airframes became stronger. Pilots developed new flying techniques. Dogfights filled the skies. The airplane had transformed from an invention into a strategic weapon. Peace brought a new dream. When the war ended, something remarkable happened. The technology built for destruction began connecting the world. Military pilots became commercial pilots. Aircraft factories turned toward civilian production. People began imagining something extraordinary. What if airplanes could carry ordinary passengers? What if continents could be connected through the sky? The dream was no longer simply flying. The dream had become travel, mail, trade, and connection. The airplane was about to shrink the world. The first passenger flights were nothing like today's experience. Cabins were noisy, cold, and unpressurized. Passengers wore heavy coats. Engines shook continuously. Navigation relied heavily on landmarks below. Flying remained expensive. Only the wealthy could afford tickets. Yet despite the discomfort, people kept flying. Because for the first time, journeys that once required days could now be completed in hours. Distance itself was beginning to lose its meaning. As airplanes grew larger, faster, and more capable, one invention would completely redefine aviation. It didn't use propellers. It didn't sound like anything the world had ever heard. Instead, it inhaled enormous amounts of air, compressed it, ignited it, and blasted it backwards with unbelievable force. The jet engine had arrived, and aviation would never be the same again. The invisible ocean. Imagine diving into the deepest part of the Pacific Ocean. Water surrounds you from every direction. You cannot see every current, yet they constantly push against your body. The atmosphere works in much the same way. Although it appears empty, Earth is submerged beneath an ocean of air. From sea level to the edge of space, our planet is wrapped in a blanket of gases nearly 100 kilometers thick. Every bird, every airplane, every parachute, every helicopter moves through this invisible ocean. Unlike water, air behaves according to the laws of physics. It flows, it accelerates, it creates pressure, and it resists motion. Long before humanity understood these invisible forces, birds had already mastered them. Every eagle soaring effortlessly above a mountain, every falcon diving toward its prey, every albatross gliding 4 hours above the ocean, is performing an extraordinary feat of natural engineering. The airplane does not fight nature, it works with it. To understand flight, we must first understand the 4 invisible forces acting on every aircraft. The 4 forces of flight.
Well before the first Wright brothers' flight in 1903, and all the way to the present day, mankind has been fascinated by taking to the skies. Once thought to be impossible, heavier-than-air flight is only a reality because of the lift generated by aircraft wings. But lift is a complicated topic, and even to this day, engineers have lengthy debates about how it's created. So what exactly is lift? When fluid flows past an object, or an object like this plane wing moves through a stationary fluid, the fluid exerts a force on the object, which can be split into a component acting in the same direction as the fluid flow, called drag, and a component acting perpendicular to the flow direction, called lift. When talking about lift, we're mostly interested in streamlined bodies like this airfoil, which are carefully designed to produce a lot of lift, but to minimize drag. Lift-producing airfoils can obviously be found in airplane wings, but also in many other applications, like wind turbine blades or propeller blades. They're also used in the wings of Formula 1 cars, which are designed to generate downforce so that corners can be taken at higher speeds. Airfoils come in a huge range of shapes and sizes. One designed for an aircraft wing won't be optimized for a propeller blade, for example. And a wing designed to fly at supersonic speeds will have a very different profile compared to one designed to fly slower than the speed of sound. Airfoil profiles can be defined using a few different parameters. The forwardmost edge of the airfoil is called the leading edge, and the trailing edge is at the back of the airfoil. Drawing a straight line between the leading and trailing edges gives us the chord line. The angle between the chord line and the flow direction is called the angle of attack. Drawing a line which is midway between the upper and lower surfaces gives us the mean camber line. Camber describes how curved an airfoil is. We can have positive camber or negative camber, and a symmetrical airfoil has zero camber. Camber and the angle of attack are important parameters that will have a large influence on how much lift an airfoil can generate. So how does a humble teardrop shape generate enough force to lift heavy aircraft off the ground? As the fluid flows around the airfoil, it creates two different types of stress which act on its surface. First, we have the wall shear stresses. These stresses act tangential to the object's surface and are caused by the frictional forces that act on the airfoil because of the fluid's viscosity. Then we have the pressure stresses. They act perpendicular to the object's surface and are caused by how pressure is distributed around it. Lift is the resultant of these two stresses in the direction perpendicular to the flow. The only way a fluid can impart a force onto an object is through these stresses. Integrating the stresses in the lift direction over the surface of the airfoil gives us the lift force. For streamlined bodies like airfoils, the shear stresses will mostly be acting in the same direction as the flow. They will make a large contribution to the drag force, but won't contribute a significant amount to the lift force. And so we can neglect them and say that the lift acting on an airfoil is caused by the way pressure is distributed around it. A typical pressure distribution looks something like this. The pressure is low above the airfoil and high below it, which creates a net force with a large component in the lift direction. If we plot the pressure profile along the top and bottom surfaces, we can see that the low pressure on the top surface is larger in magnitude than the high pressure on the bottom surface. So the suction pressure on the top surface is what contributes most to the total lift force. We can also see that the majority of the pressure difference is coming from the forwardmost part of the airfoil. In truth, there's nothing particularly special about the shape of an airfoil that allows it to generate lift. Any object that creates an uneven pressure distribution will generate a force in the lift direction, like a flat plate at an angle relative to the flow, for example. Airfoils are just optimized shapes that have been carefully designed to have high lift-to-drag ratios. Without a difference in pressure above and below an object, there can be no lift. A symmetrical body, like this bullet, doesn't generate any lift force because there's no pressure difference around it. So we know that lift is caused by the pressure distribution around the airfoil. But where does the pressure distribution come from? The answer to this question is complex, and there's much debate about the best way to explain it in a concise way. We can broadly split the different explanations into two groups, those based on Bernoulli's principle, and those based on Newton's third law. Bernoulli's principle explanations focus on the velocity of the fluid. If we look at how fluid flows around the airfoil, we can see that close to the leading edge, there's a point where the fluid velocity is reduced to zero. This is called the stagnation point. Outside of the thin boundary layer surrounding the airfoil, the fluid flowing above the stagnation point over the top surface of the airfoil travels faster than the fluid traveling over the bottom surface, as we can see from these particles. Bernoulli's principle tells us that when the velocity of a fluid increases, its pressure must be reduced, which is just a statement of the conservation of energy. This means that the increase in velocity above the airfoil creates an area of lower pressure, and the reduction in velocity below it creates an area of higher pressure, and this pressure difference creates the lift force. But then, we need to explain what causes the difference in velocity. One explanation is that the geometry of an airfoil causes the flow to be pinched together above the airfoil, but not below it. Because of the conservation of mass, this results in increased velocity above the airfoil. A more complete but less intuitive explanation for the difference in velocity is based on the concept of circulation. The flow around an airfoil can be thought of as the superposition of idealized uniform irrotational flow and circulatory flow. Without circulation, the flow around the airfoil would look like this. This is clearly non-physical, since the fluid can't turn such a sharp corner at the trailing edge, and so the airfoil must be generating some circulation. If we impose a condition that says the flow above and below the airfoil must be parallel when leaving the trailing edge, we can calculate the exact amount of circulation that must be generated by the airfoil to do this. This is called the Kutta condition. Circulation has the effect of accelerating the flow above the airfoil and delaying the flow below it, which gives us the explanation we need so that we can apply Bernoulli's principle. What about the explanations of lift that are based on Newton's third law? These don't consider the velocity above and below the airfoil, but instead look more generally at the behavior of the fluid. If we look at a wider area, we can observe that the effect of an airfoil can be felt far beyond its immediate vicinity. Upstream of the airfoil, the flow is being swept upwards, which is called upwash, and downstream the flow is deflected downwards, which is called downwash. A very large volume of air is being displaced by the airfoil. Newton's third law tells us that for every action there is an equal and opposite reaction. The airfoil must be imparting a force on the air to create the downwash, and so based on Newton's third law, there must be a corresponding reaction force acting on the airfoil. In other words, an airfoil generates lift by turning the incoming air downwards. We can use the concept of circulation again, this time to explain how the upwash and downwash are created. In summary, a lift force acts on an airfoil because of the pressure distribution around it. The exact cause of this pressure distribution is complex and can be explained in several different ways, which approach the problem from different angles. Explanations based on Bernoulli's principle and on Newton's third law provide valuable insight into how lift is generated, although both approaches have limitations, partly because they're based on cause and effect relationships. The problem is that there isn't always a clear cause and effect relationship between the different phenomena which are involved in generating lift. Whether we're talking about the fluid velocity, the pressure distribution around the airfoil, or the downturning of the fluid. In reality, all of these things are happening simultaneously and are mutually interacting. Nevertheless, these explanations are useful and can lead to a more intuitive understanding of lift. We can easily imagine, for example, that increasing the camber of an airfoil will allow it to deflect a larger amount of fluid, and so will increase the lift force. The same is true for the angle of attack. Increasing the angle of attack deflects more fluid and increases lift. However, there are limits to this logic. Once the angle of attack reaches a certain critical value, we can observe a sudden decrease in the lift force. For this airfoil, it occurs at around 16 degrees. At this angle of attack, the boundary layer is no longer able to remain attached to the airfoil, and it detaches from the surface, creating a wake behind it which affects the pressure distribution around the airfoil, significantly reducing lift and increasing drag. I covered flow separation in detail in my video on aerodynamic drag. The sudden reduction in lift is called stalling, and it can be very dangerous for aircraft. Different airfoil shapes can have drastically different lift characteristics. This airfoil is cambered. If an airfoil is symmetrical, and so has zero camber, the lift force will be zero for zero angle of attack. Aerobatic aircraft usually use symmetrical airfoils since they allow planes to fly upside down more easily. Lift is generated by lifting the nose of the plane to create an angle of attack. Modern aircraft wings are equipped with flaps and slats, which allow the shape of the airfoil to be adjusted and optimized for different phases of flight. During takeoff, for example, you want high lift. Extending the flaps increases the camber of the wing, which increases lift, and so flaps are extended during takeoff. But the extra lift comes at the expense of increased drag, and so the flaps are retracted when cruising, since high lift is no longer needed and drag should be minimized to improve fuel consumption.
Air traffic control.
From the start of any flight, it's under the watch of the Airport Traffic Control Tower, which provides clearance for takeoff, then follows the departure on the first few miles of its flight. When the aircraft leaves the immediate airport environment, it is handed off to a Terminal Radar Approach Control Facility, or TRACON. Controllers at TRACONs handle traffic for a radius of about 40 miles and up to 10,000 feet high. Once the aircraft climbs beyond the TRACON's airspace, it is handed off to an Air Route Traffic Control Center. There are 24 centers across the country in the Pacific and the Caribbean, each handling a designated segment of airspace. At the end of the journey, the opposite process happens. The aircraft descends down to the receiving TRACON, then to the airport tower as it lands and taxis to its gate. Each major airport has a tower where controllers monitor all aircraft taxiing, taking off, and landing at the airport. Each control tower owns the airspace up to 3,000 feet above and a radius of 5 miles around the airport. Controllers in TRACONs monitor aircraft in departure, descent, and approach. TRACONs can handle air traffic for several different airports in an area. The 24 centers monitor aircraft during cruise altitude. Controllers here sometimes handle dozens of flights at once.
Flying through the clouds. Here's something surprising. Modern pilots do not need to see the ground to fly safely. In fact, commercial aircraft routinely spend much of a flight surrounded by clouds where there is no outside visual reference. How is that possible? Because today's aircraft rely on an extraordinary combination of instruments, navigation systems, and pilot training. Inside the cockpit, pilots can instantly see their altitude, their airspeed, their heading, their climb or descent rate, their attitude relative to the horizon, weather radar, navigation information, and traffic nearby. Even if the outside world disappears completely, the instruments continue providing an accurate picture of the aircraft's position and motion. This is why aircraft can safely fly at night, over oceans, and through thick cloud. The pilot isn't guessing. They're reading an incredibly sophisticated picture of the flight. Landing in zero visibility. Now imagine the runway is hidden by dense fog. Visibility is almost zero. From the passenger cabin, all you see is white. Yet moments later, the wheels touch the runway with astonishing precision. How? Many major airports are equipped with an instrument landing system, often called ILS. This system transmits highly accurate radio guidance that helps aircraft align with the runway centerline and descend along the correct glide path. Combined with onboard instruments and, in some aircraft and conditions, certified automatic landing capabilities, it allows safe approaches even when visibility is severely reduced. By the time the runway lights finally emerge from the fog, the aircraft is already exactly where it needs to be. To passengers, it feels almost magical. To engineers, it's decades of technological innovation working perfectly together. For more than a century, engineers have chased one goal: to make aviation safer, faster, cleaner, and more efficient. And today, that journey is far from over. The airplanes of tomorrow may look nothing like the ones we fly today. The next revolution has already begun. The next frontier. More than 100 years have passed since 12 seconds of flight changed human history. Today, more than 100,000 flights take to the skies every single day. Millions of passengers cross continents. Fresh food travels across oceans overnight. Emergency medical supplies reach disaster zones within hours. Families separated by thousands of kilometers can reunite in a single day. The airplane has become so ordinary that we sometimes forget how extraordinary it truly is. Yet, the story of flight is far from over. In laboratories, universities, hangars, and research centers around the world, engineers are once again asking the same question the Wright brothers asked over a century ago: how can we fly better? For decades, jet fuel has powered global aviation. It is energy-dense, reliable, and capable of carrying aircraft across entire oceans. But it comes at a cost. Modern aviation contributes to global carbon emissions, and as air travel continues to grow, reducing its environmental impact has become one of the industry's greatest engineering challenges. Rather than abandoning flight, engineers are reinventing it. One solution already taking shape is sustainable aviation fuel, often called SAF. Unlike conventional jet fuel, SAF can be produced from renewable or waste-derived sources, and depending on how it's made, can significantly reduce life cycle carbon emissions. Many airlines are already using SAF blends on commercial flights. It's not the final answer, but it's an important step. Electric cars have transformed the automotive industry. Naturally, people ask, why not electric airplanes? The answer lies in energy density. Modern batteries simply store far less energy per kilogram than aviation fuel. For a family car, that's manageable. For a passenger aircraft flying thousands of kilometers, it's an enormous challenge. Yet progress continues. Several companies have successfully flown small electric aircraft. These airplanes are quieter, produce no in-flight exhaust emissions, and require far fewer moving parts than traditional engines. For short regional flights, electric aviation may become increasingly practical in the years ahead. For long-haul travel, the challenge remains. Another possibility lies in the most abundant element in the universe, hydrogen. When used in a fuel cell, hydrogen can generate electricity while producing water as the primary byproduct. It also has an impressive amount of energy by mass. But there's a catch: hydrogen is difficult to store. It requires extremely cold temperatures or high-pressure tanks. Its tanks are much larger than conventional fuel tanks. Designing an airliner around hydrogen, rethinking the aircraft from the inside out. Manufacturers and researchers are actively exploring whether these challenges can be overcome. If they are, hydrogen could reshape the future of aviation. The return of supersonic flight. In 2003, the retirement of the Concorde marked the end of commercial supersonic passenger travel. For the first time in decades, flying faster than the speed of sound became a memory, or so it seemed. Today, a new generation of engineers is attempting something once thought impossible: to make supersonic flight practical again, but this time quieter, safer, and dramatically more efficient. Experimental aircraft are exploring new aerodynamic shapes, designed to reduce the thunderous sonic boom that once limited supersonic travel over land. If successful, a journey that currently takes 8 hours could someday take 4. The dream of shrinking the world even further lives on. The sky isn't the limit. More than a century ago, two bicycle mechanics stood on a lonely beach in North Carolina. Their machine flew for just 12 seconds, only 12. But those 12 seconds proved something humanity had spent thousands of years believing was impossible: we could fly. Since then, we've crossed oceans, we've connected continents, we've carried millions of people through the sky. We've flown faster than sound, reached the edge of space, and built machines capable of carrying hundreds of people thousands of kilometers in a single journey. And yet, The most remarkable part of aviation may not be what we've already achieved. It's what comes next. Electric aircraft, hydrogen propulsion, sustainable fuels, supersonic travel, more efficient engines, aircraft that are quieter, cleaner, and perhaps completely different from anything we recognize today. Because the story of flight has never really been about airplanes. It's about curiosity. The refusal to accept that something is impossible simply because nobody has done it before. From watching birds to building wings, from fragile gliders to jet engines, from 12 seconds above a beach to millions of flights every single day. The sky was never the limit. It was only the beginning. This is Circuits and Crank, and if you want to understand the machines shaping the world around us, I'll see you in the next one.